Hello everyone and welcome back to Zaki Educational channel. So this is the part 9 Mark Booster series of GATE Environmental Science and Engineering, and here today in this video we will discuss about one of the important topics of environmental chemistry which is given in the syllabus of the GATE Environmental Science and Engineering. So in the syllabus, in the environmental chemistry part, the main topic which is related to the soil chemistry is cation exchange capacity. So today we'll learn everything about this. So I hope you are ready with the notes. Try to note down all these points because they are going to be very helpful in the examination. So let's start with the definition first. So what is meant by cation exchange capacity? So cation, we all know those who are having the positive charge on them, the ions, so they are known as cations. And here, what is this cation exchange capacity? So this cation exchange capacity is actually the capacity of the soil. So let us assume this is the soil profile, and the capacity of the soil to hold or adsorb the exchangeable cations is known as cation exchange capacity. So what is this hold on or adsorb? So on the surface of the soil, how much quantity or what is the capacity of the soil to hold the cations, that is known as the cation exchange capacity. So it is the fundamental soil property, and here it is also can be said that it is the ability to hold on the essential nutrient, because these elements are composed of macro or micronutrients which are essential for the plants. So from soil they will be taken by the plants, so that's why this is very important. So it can be said that it is the ability to hold on the essential nutrients and provides a buffer. Yes, provides, which provide this cation exchange capacity, these ions, they provide a buffer against soil acidification. Yes, what is this buffer? Buffer means they maintain the pH of the soil if it is less or more. So they are the important part. And here actually we should know that the total quantity of negative surface charge is equal to the total quantity of positive surface charge adhered to them. Yes, why? Because if you can see in this picture, here these are the negative charges. So number of negative charges will be equal to the number of cations those are attaching to the soil, that is the adsorbing to the soil surface. So it can be also said the total quantity of negative surface charges. Similarly, here if you can see the sum of cations, that is base cations plus acid cations, will give the total value of cation exchange capacity of any soil. So what are these base cations and acidic cations? So these are very simple. So you know, for example, let us take an example of base. So base means we will take for example of NaCl. So here NaCl, Na plus is the cation part. So in this base, Na plus will be considered as the base cation. If you are taking the example of acid, so acid, first of all we will take the example, simple example is HCl. So in HCl, the H plus is the cation part, so that will come under the acid cation. So including all these two, that is base cations and acid cations in the soil, we will get the cation exchange capacity of the soil, and accordingly we will be able to say whether that soil is fertile enough for the plant growth or not, what we have to add, whether we have to add some acid or alkali to make it suitable for the plant's growth. So here the base cations include calcium, magnesium, potassium and sodium, whereas the acid cations, for example, we can include hydrogen and aluminium cations. So now let us know what is the unit of this cation exchange capacity. So unit of the CEC is milli equivalent per 100 gram of soil, so that is the unit, and it is used as the milli equivalent, not used instead of mass or weight, because charge is involved here, that is cation's charge you are talking about, that's why it is taken in the form of milli equivalent per 100 gram of soil. Let's move to the next slide, and here cation exchange capacity actually influences the potential of available nutrient supply. So from the cation exchange capacity, you will be able to say whether the soil is having the potential enough for the nutrient supply to the plants or not, as I have said earlier. So now this table is very important, you should note it down. So this is the average typical cation exchange capacity of the different soil textures. So light colored sands, so the sands which are having less amount of clay. Yes, this cation exchange capacity is dependent on the clay quantity of the soil. So here they are having least clay, that's why they will be having least typical CEC, that is cation exchange capacity, with the range of 3 to 5. As the clay particle increases, clay concentration increases in the soil texture, from loamy to silt loam, clay and clay loams, to the organic soils which are having more amount of clay and more amount of cations, these typical CEC increases from 3 to 5 to 50 to 100. So you should note it down. I'm not going to tell all of this because it will be very boring. Let's move to the next slide. And this is also important. The type of clay soil, it can be asked in the question in the examination, that kaolinite type of clay soil is having the lowest cation exchange capacity of 3 to 15 milliequivalent per 100 gram, followed by the illite, that is 15 to 40 milliequivalent per 100 gram. Then the maximum is with the montmorillonite, that is the clay type, with 80 to 100 milliequivalent per 100 gram of soil. Similarly, as we have discussed, sandy soil, fine sandy loam soil, clay loamy and clay soil, these are the ranges. So no need to know all these things. You should know that it increases from sand to clay. And in organic matter, particularly if you are considering, the CC cation exchange capacity goes from 200 to 400 milliequivalent per 100 gram of the sample, that is here it is organic matter. Let's move to the next slide. Here one more term you should know, base saturation. So what is this base saturation? Actually, when we have calculated the CC, that is cation exchange capacity, we can find out the base saturation. Yes, only considering the base cations dividing the CC, we will get the base saturation of the soil. So here, as you can see, here the high cation exchange capacity, this soil is also having high cation exchange capacity. But here base saturation can vary. Yes, in this soil there is low base saturation, but in this soil there is high base saturation. Why? Because in the left side soil profile it has the less base cations, but in the right soil profile it has the more base cations. But here actually the base saturation increases as the pH increases. So it is very basic. pH increases means it is going beyond 7. That means it is going in the alkaline range, 8 to 14. That's why it increases. That is the base saturation increases as the pH of the soil increases. Coming to the calcium saturation. Yes, calcium saturation is also one of the important term you should know. So it is also simple. We have to find out CEC, that we will be discussing in the last segment of this video, and it should be divided by the calcium percentage, that is the calcium ions, getting calcium saturation. So it is also used as the management tool for some growers, that is those who are growing the plants. They are calculating this calcium saturation, which is very effective. And then here it is same example is taken and it is considering here calcium. So those will be having more calcium cation will be having the more higher saturation, base saturation of calcium. Here there are more, as you can see, 3 times calcium ions, but here example has taken only 2 times calcium ion. That's why they are having low base saturation, that is low calcium saturation. For magnesium, if you want to calculate magnesium saturation, we can find out by dividing magnesium by CC, that is cation exchange capacity. So after that also we can find calcium by magnesium ratio based on the calcium and magnesium saturation percentage. So you can also find the ratio between calcium saturation and magnesium saturation, which are also useful for analyzing the soil quality. Let's move to the next slide. Now it is the time to calculate the main thing, the boss, that is cation exchange capacity. So how it will be calculated? First of all, we have to do the laboratorical work to find the quantity of the elements present. So you have to do soil test, and that to be in parts per million. So we'll discuss in the next slide, no need to worry. Then we will calculate using this same formula which we discussed in the first or second slide. By adding the base cation plus acidic cations, will get the total CC, that is cation exchange capacity of any soil. So let us see how to calculate. Before that, we will be dealing about the base cations. So from here, periodic table, we have taken 4 elements, that is 4 base cations, that is Na plus, Mg plus, K plus and Ca plus. So let us analyze them. So if we are going to analyze them, first of all, we have to calculate in equivalent, that is milli equivalent. So for that, equivalent is to be multiplied or converted into milli equivalent. For that we have to multiply with 1000. So equivalent, if we are getting, we have to multiply by 1000 equivalent. By equivalent it will be cancelled, so 1000 milli equivalent it will be when we are converting equivalent to milli equivalent. Next is milli equivalent, we have to set for 100 gram of soil. So what is this? I will tell you with the help of this table. So here let us take an example of calcium only. So calcium atomic weight is 40. Calcium charge, that is valency is 2. As you can see here, valency of calcium is 2 valence electron. Then we have to find out the gram equivalent weight. Yes, how to find out? This is very simple. Simply divide atomic weight by the valence charge, that is 40 by 2 will give 20. Then to find out the CC, we need to find a conversion factor. Yes, How to calculate the conversion factor? It is very easy. So simply this 10 value which we are talking earlier, we have to multiply with the gram equivalent weight. So how much will be the gram equivalent weight of the element? We have to simply multiply it with 10 and then we will get the conversion factor for calculating CC. Similarly, for magnesium, we'll find out the gram equivalent weight, that is the atomic weight 24 divided by 2, that is charge of valence. So it will be 12, then multiplied by 10, we'll get the conversion factor as 120, 390 and 230 respectively for potassium and sodium. So here what I wanted to tell you that, first of all, to convert it into equivalent to milli equivalent, we have to multiply anything with the 1000. Then 10 will be the milli equivalent set for calculating for 100 grams of soil, because 1000 milli equivalent divided by 100 gram will be 10, which will be used as the multiplication conversion factor. So here gram equivalent weight will calculate, then multiply with 10. Let's move to the next slide. In the next slide, here what we will do is, after using this conversion factor, what we have to do? We have to simply find the milli equivalent per 100 gram of soil per individual cations. Yes. So how it will be calculated is very simple. Let us assume in a soil test soil sample we got 2000 ppm of calcium. So we should not get confused that how to calculate. These are different things, how to calculate calcium, magnesium, potassium and sodium in the soil. So I made a separate video. You can check the link given in the description. So let us assume there is 2000 parts per million of calcium in the soil. Then what happened? We have already calculated for calcium that milli equivalent per 100 gram soil is 200. How? By multiplying 20 into 10. That is the equivalent factor, that is the equivalent weight into 10. We have got 200. To find milli equivalent per 100 gram of soil, we have to simply divide the soil test ppm by the conversion factor, that is 200 here, and we'll get 10. So these are different things, this one and this one. This one is the conversion factor which you already calculated in the previous slide. This one is the value which we will get from the analysis of the soil testing in parts per million. Simply we will divide and we'll get individual milli equivalent per 100 gram soil of individual cation, that is here base cation we are discussing. Here we are base cation discussing. Next is, if some soil test value is not in ppm, that is parts per million, but it is in lb per acre, then we need to convert this lb per acre to parts per million by simply dividing the value by 2. For example, if the value is in lb per acre is 4000, then we will divide it by 2 and we will get in ppm, that is 2000. Then we will proceed likewise and we will get the milli equivalent per 100 gram soil of that particular base cation. Let's move to the next slide. So here what we have done is, we have now calculated the acid cations. Yes, as you can see, this table is added. So here what we have to do, acid cation means exchangeable acidity we have to find. So that can be of H plus, Al3 plus or NH4 plus. And here what we will do is, simply we need to take a buffer pH for the analysis of that soil, and according to the buffer pH we have to equate according to the conversion equation. So what is this equation? This equation is 12, which is standard taken, multiplied by 7, that is the neutral point, minus the buffer pH taken for the soil analysis. So that value will differ from soil to soil and we have to add it in this portion to get the value, that is 4.8. So 12 multiplied by 7 minus 6.6 will be 4.8. So remember the formula is 12 multiplied by 7 minus 6.6 to get 4.8 here in case. So then that will be the milli equivalent per 100 gram of soil, that is the cation exchange capacity of the acid cation. And one most important thing you should note, that if the buffer pH is taken above 7 or 7, then no need to calculate this acid cation. Simply add all this base cation and that value will be the cation exchange capacity of the soil. But if the buffer is less than 7, as here in this case it is 6.6 we have taken, then we have to calculate the acidic cation, that is 4.8 here coming with the formula 12 into 7 minus the buffer taken. So in that case we have to add this 12.4, that is base cation exchange capacity, and with the addition with the acid cation exchange capacity. So here by adding these two, 12.4 plus 4.8, we will get the value as 17.2 milli equivalent per 100 gram of soil as the cation exchange capacity of any soil. So this soil which we have considered, the value will be 17.2 milli equivalent per 100 gram soil, not any soil, for this soil for these values. So I hope you are able to understand. And in the next class, we'll discuss about the calcium saturation and magnesium saturation. They are very easy topics. So stay tuned for the next video. And if you like this, don't forget to subscribe the channel to get further updates.